All right, so let's do the linear things. Linear curves. So why linear? Well, this is because of the nature of calculus. Again, calculus is a method of reducing nonlinear problems to linear problems. So we are studying linear curves first. Whatever we are going to study, curves, surfaces, all the objects we will study, we will start with linear objects, even equations, right? And then we will progress to nonlinear using differentiation. So what does it mean to be linear? What does it mean for a function to be linear? Now I have a function of two variables. I'm using algebraic language, and what does it mean to be linear? It means it is in the form a times x plus b times y plus c, where what? X and y are those variables, right? And a, b, c are constants. All right, what should I be interested in the most from calculus point of view? What do you think? The rate of change, yes. So let's start with the change. So how do I compute the change of that function? Let me do some computations here. Change of f. Well, in order to talk about the change, I have to pick 2 points, right? So let me pick a point x0 and y0. Thinking geometrically, that's 1 point on a plane. And I want to compute the change from that value, f of x0, y0, to the value f at x0 plus delta x, y0 plus delta y. And we need to change x by some value delta x, change y by delta y. And, well, what is that? Well, that's simply a difference, right? F of x0 plus delta x, y0 plus delta y, minus f of x0, y0. How do I compute? Well, I know the formula for f, so I substitute. I substitute these two to get a times x plus delta x plus b times y plus delta y plus c, and I subtract the whole value of f at x0, y0. And those should be x0 and y0, of course. And that will be a x0 plus y, well, b y0 plus, now let me simplify, or c cancels. So that difference is a times x0 plus a delta x plus b times y0 plus b delta y. And I subtract a x0 plus b y0.
Is it minus by0?
It is minus by0, yes. Thank you. And is it better with minus? It is better because something cancels, right? by0 cancels, ax0 cancels. And the whole thing is a times delta x plus b times delta y, which looks like linear equation and dot product. Yes, it looks like a dot product. And if you are to make this a dot product of two things, what would you pick for those things? Well, a and b, right? And delta x and delta y. So the change of x, well, the change of f is equal to the dot product of those two things. And now the advantage of that is that now we can translate that into algebra. Oh, sorry, into geometry. Because dot product is, in some sense, geometric concept. But unfortunately, there is no way to visualize the dot product itself. That's the fundamental problem with the dot product. it tells you pretty much nothing visually. So let me try to translate that into geometry. I'm looking into a plane, right? I have a point x0, y0. I have another point on a plane, x0 plus delta x, comma y0 plus delta y. And now I'm willing to call these points, let's say P and Q. And then what does it mean to change from P to Q? Because this is the kind of change we are talking about, right? That means somehow to consider a vector, right? So this vector PQ, which is about transition from P to Q, what are the coordinates of that? Well, if you do simple subtraction, it's delta x, comma delta y. So this is the vector we have there in the formula. So abstractly, if you think about a function that assigns a number to each point on a plane, if you want to change the values, change the points, well, that's the change involved in the plane, and the change involved in the values of f, this delta f, is exactly the dot product of AB times that vector PQ. And as I said, the problem is that we don't see that dot product. So how to visualize that formula? How to interpret that geometrically? Well, the thing we can actually visualize is that product divided by something. Well, let me introduce the vector here. Well, let's suppose that is the vector AB. Okay. There is no way for us to see what the dot product is, but if I divide that by magnitude of PQ, and of course I have to divide the left-hand side as well, just to keep equality. Well, that makes sense geometrically. What is that? Do you recognize that fraction? Dot product divided by the magnitude of one of the vectors? That's component, yes. That is component of which vector? Of the vector AB. With respect to the direction PQ. All right, so, well, we gained this geometric interpretation of the right-hand side, but we changed the left-hand side. Can we still understand what left-hand side is? Because it would be best to understand both sides. Well, think about that, but let us visualize this component of AB with respect to PQ. Can we see that? What do you do to see the component of this vector AB with respect to that direction PQ? Well, you just project, right? So this is exactly that number. That's how large it is. This is component of the vector AB with respect to the direction PQ. All right, so the right-hand side is immediately geometrically visible. What's the meaning of the left? I moved from this point P to the point Q in the domain of the function. I looked at the change of the function, and then I divided it by the magnitude of the change of the variable P. Right? What is that? What kind of ratio is that? Change of the function divided by the change of the independent variable. Isn't that the ratio you look at calculus all the time? Isn't that the rate of change of the function f? That's exactly what it is. So you see, the point is that the change itself cannot be visualized. The rate of change can. That's the advantage of rate of change of the derivative over just change. So this is the rate of change in case of linear function, right? So this is a special case when f is linear. I don't need any limit here. No matter how I change that, the ratio will be equal to the rate of change, in some sense. So, rate of change of f at this point, at the point x0, y0. Is that rate different if I switch from P to some other point? Well, let's play with that. What if I switch from P to a point there? What would be the rate of change of my function in that direction? Well, the rate of change is going to be projection of this AB vector onto that direction, right? So the rate of change is quite different. Now, what if I want to change from that P to another point on the same line? What if I want to change from P to this point? What will be the rate of change? Well, it will be exactly the same. So the rate of change is going to be the same along the whole line here. No matter how far you go along this line, the rate of change is the same. Change is different, right? The further you go, the more change you have. Isn't that what you expect? The more you change x and y in the formula, the more you change the value. But if you go in the same direction, the rate of change stays the same. Well, of course, if you go in a different direction, the rate of change changes. It might be different.